Hey everyone, how are you? You guys still awake? Yeah, okay. Well, I'm going to put you to sleep. How many people like looking at hex? Yeah, that's right. That was more hands than I was expecting. That's good. Okay, so my talk is really long, and I can't say it all because I'll buffer overflow or something. I don't know. I don't know what I was thinking when I submitted this talk, because I thought I could go from like beginning to end, in 60 minutes, and we'll see what happens. I'm Panda Tracks. Let's see. There we go. Who am I? I'm Panda Tracks. I'm a lead security engineer at a big company somewhere around here. I like trying to figure out how things work, and I like breaking things. I didn't put that in the slide, but I do like breaking things, and we're going to learn how to break some stuff today. And this is not my profession at all. I do this for fun, even though people have told me that I probably should look for work in this field. What I actually do is I do malware reversing for a career, but this is kind of similar. So I wanted to talk about like how to get started in this field. I think that a lot of people don't get started because they think, man, there's hex involved, it's hard, or there's assembly language, right? It's really hard. It's not really that hard. I think it's kind of like, you just have to get your feet wet, and then you realize, you know what? The water is actually pretty warm. I'll get into it a little bit more. And there's a lot of literature out there, and I think that one of the problems that I've seen with the literature is it dives in real deep, right? Really fast, and then it just scares you off. Like my brain would hurt after reading a couple pages, and I'd have to walk away. And then like a year later, I'd be like, wait, I remember I wanted to learn about that. So today I hope that I can like give you that push into the water, and hopefully it's not too deep, and you guys can start breaking some stuff too. And be like, if you guys have questions afterwards and you're interested in reaching out to me with questions and stuff, I'm always open to like sharing what I know. And hey, if you know something more than me, please let me know, because I am all about learning. I would love to share information. So when you get started, what do you need? It makes it a lot easier if you have some type of virtualization software. VMware is great. You really probably want to have something that can take snapshots, right? Because it's a real bummer when you have to go and like start everything over again, over and over and over again. If you can take a snapshot and go back to the snapshot quick, it makes life a lot easier. You need a victim, right? Today, a Microsoft app is going to be a victim because it's just so easy, right? Not because it's on Microsoft, right? Microsoft is great. But it's because this particular piece of software is just like, I think it was written just to be pwned. I don't know. So, and you need a debugger, right? And some other tools. I'm going to show you that there's some other tools that we're going to use, some really, really cool tools. So I am not very good with slides, and we're not going to be doing a slideshow here. I did pray to the demo gods this morning, and I'm hoping that they heard my calls, because this is an entire demo for 60 minutes with some slides thrown in. So what do we have here? We have a Python script. I hope everybody can see it way in the back. If not, please move forward. There's lots of space down here. And I'm using Python. If you are a Ruby person, use Ruby. If you are a C# person, more power to you, man. I use Python just because I don't know. I used to be a Perl guy, and then one day I woke up and realized that everybody saying that Python was easier was really right, and I decided to change my ways. So I have a script. This is how you want to start out with a buffer overflow. What do we have? We're gonna like create 100 A or 1,000 A. Sorry, I was missing a zero. just 1,000 A's, right? Why A's? Capital A's? Why? I have no idea. That seems to be the convention, right? Like I was telling the class I was teaching yesterday, I would have chosen capital B's. For those that were not in my class, why would I choose capital B's for the thing I want to put in there? Anyone? Capital B's. Okay. Capital B in hex is 42. It's the answer to the life of the universe and everything, right? But I know, right? Yeah, that's true. So I'm using A's just because it's convention. You can use whatever you want. If capital B is 42, what's capital A? Anybody? 41, right? Exactly. So we're gonna just create a file. This particular piece of software is a movie player, right? And the movie player needs a playlist. We're creating a playlist, obviously, with a bunch of A's in it, right? Yeah, that's right. Okay, so I'm gonna just go and run that script. I called it exploit_EIP. And it created a file. It's my playlist. Let's check it out. Look at that, all those songs in that playlist, right? Looks good to me. Or movies. I'm sorry, it's a movie player. And I'm going to go over. So I have 2 boxes, right? You need 2 boxes, or I need 2 boxes. If you can run Python or whatever scripting language that you use on a Windows box, you could probably get away with just using 1 box if your victim is, the same platform as what you're developing your code in, right? But I'm using Kali as 1 box. I'm using my Windows box, obviously, for my victim. I'm using a shared folder between the 2 so that I can just create the file on one side and then execute the exploit on the other. So this is my exploit. This is very complicated, right? This is what I'm talking about. Let's get our feet wet. Let's dip our toe in, right? It's just a bunch of A's. Well, come to find out with this piece of software, let's fire this piece of software up. I'll pay later. Okay, I'm going to open it up. Okay, here's the file. Okay, and I'm going to open it up in a debugger, Immunity Debugger. Okay, Immunity Debugger is a debugger based on Ali Debug. Lots of people know about Ali Debug, right? Because we use it for malware reversing. Immunity Debugger is an awesome debugger as well. It's based a lot, like I said, on Ali Debug. The nice thing, the reason why I'm using it is because it supports Python, right? And there is this great gentleman whose name is Peter, and I cannot say his last name, but he goes by the name Corlan, and he wrote Mona. And Mona is a great tool to help you figure out, how to write these exploits. So I'm going to go and attach my a debugger to the application and see what happens, right? So I'm going to start it up, go, and the application crashed. First, what I need to do is I need to go and accept some exceptions that have nothing to do with the overflow that I just did to this. But you'll see right now that there's a couple things that have happened, right? Do we see something that might be noticeable on the screen at the moment? Yes, we see some 41s. There's lots of 41s. There's about 1,000 of them. Actually, there's probably multiple thousands of them, right, in memory right now. The other thing that I've done is I've overwritten EIP. EIP is the instruction pointer. It tells the application what it's supposed to do next. Guess what? There is no instruction at memory address 41414141. Yeah. So what just happened? I just crashed the app just by sending it A's. Right? That's it. I'm done. How'd you guys like my talk? Okay, thanks. Okay, let's develop this into something more meaningful, right? Okay, so we're gonna go, and you know what? I'm just gonna fix my screen here. Yeah, I made it smaller. No, oh, for some reason it's not really doing what I wanted. Okay, so so what I need to do now is I need to figure out how far into my payload I have to go before I overwrite EIP, right? Because I really want to control EIP, because if I can control EIP, I can tell the application what to do, right? It becomes mine. So what I'm going to do is I'm going to use a tool that lots of you know. How many red teamers are in here? Raise your hand high. Be proud. That's right. Okay. I'm not a red teamer, but I aspire to be one. Metasploit is a great tool, and what we're going to do is we're going to utilize a function of Metasploit called pattern create. Man, sorry about this. Having it plugged into this projector is messing with my. Okay, here we go. And if you go and use it, what it does is it creates a cyclical pattern. Actually, you know what? Before I do that, let's say how big I want it, because that's going to be really bad. Okay. Yeah, sorry guys. There, so you can see it. Oh, you gotta be kidding me. Oh, can you? Oh, good. Okay, I'm glad you can see it. I can't see it, anything. Okay, there we go. I can see it now. Okay, I'm gonna do this again with 1,000 characters. There we go. Okay, so what it's done is it's created a cyclical pattern, right? There's no repeating pattern in this, right? I think there is probably a limit as to how big the size of a pattern you can create, but for our purposes here, we only need a pattern that's 1,000 bytes long. So what I'm going to do is I'm going to throw that into my script real quick. Okay. And I'm going to replace my 1,000 A's with my pattern. So okay. So here we are. We've got our pattern. I'm going to run it again. Oop. This went better in my head. Okay. Okay, so now if you look at the file, right, we've just got this pattern. Okay, so I'm going to go back over to my Windows machine, and now I'm going to try to figure out how far off, or how big the offset is before hitting EIP. Opening it up. Okay, I've attached. I'm going to crash it again. And crashed it again, right? This has caused the crash. Now look at and see what's in EIP. We have we don't have 4 1s anymore, right? Because I didn't send all A's to it, capital A's. But I do want to know what this represents, how big of an offset it is. I can go back and take this hex that is in EIP right now and ask Metasploit what the offset is by using pattern offset. So pattern offset is the partner to pattern create. But I'm going to save some time, and I'm going to use Mona, right, to figure it out. So within the immunity debugger, I can just go down to the bottom and say, hey, Mona, I want the pattern offset of 37694136. Okay? An offset of 260 bytes. That's all. And then I have control of EIP. So I'm going to go back. I'm going to change my script again. I'm going to get rid of this pattern. And what did I say? 260 60 bytes, right? So pre-EIP equals 260 bytes. So this time I'm going to change this to pre-EIP, right? But hey, you know what? I also want to make sure that I am overwriting EIP. So I'm going to put Bs, 4 Bs in, because that will fill out BIP, right? Because I need 4 bytes for this register. And then I'm going to fill the rest of it with, what, Cs? Yeah, Cs sounds good. So I'm going to say tail size equals total minus the payload size, right? Let's see, the length of the payload. And then I'm going to say pretty much just this up here, same thing. And I'm going to put C's in here and change this tail size. So we're going to have this file. Oh, yeah, what did I do? Yep, that's right. Thank you. Did I miss another one? Oh, yeah, nice. Thanks, guys. Okay. This is the reason why you always have to pray to the demo gods. Okay, perfect. Right? So hopefully the B's will show up in EIP. Okay. Go back over and start it up again. So there's a lot of repetition to this, right? You're going to be going back and forth until you get what you want. Oh, yeah. Set that puppy up. Yeah, there you go. Awesome. It's very hard with the screen the way it is. Okay. Okay, so now what have we done? We verified that indeed we have 42s in EIP. Okay. The other thing to note is I want to look at the stack. Down here, where this blue line is the stack, right? And you can see how I have A's above the B's. The B's at memory address 0018F204 is apparently where EIP is being pulled off the stack, right? More than likely, there's a ret that occurred that caused this to happen, right? There's a saved EIP that's supposed to be at that particular memory address. The function is finishing, going back to the calling function. And instead of going back to where it's supposed to, I told it to go to BBBB, right? Hex address 42, answer to life of the universe and everything, right? But then also on the stack, you also see C's going down further, right? I have control of a lot of the stack right now, right? So I can do a lot of stuff here. So the next thing I want to do is I want to do something with this, man. What can I do? What can I do from here? I can go, if that was a ret that told the application to go someplace else, why don't I go and try to figure out where I want it to go, right? Let's see where we can tell it to go, right? Okay, so Mona has this great tool called jump. And you can say, Mona, I want to know where all of the addresses in this memory space is that includes a jump. And I'm very interested in a jump ESP. Why a jump ESP? Because ESP is highlighted in blue right now, right? I have control of that memory address, right? I can tell it to go someplace as long as I put that memory address in that spot where that blue line is, because that's where ESP is pointing. So I'm going to go and ask Mona for that. I'd say, Mona, jump minus R, because it's a register, ESP, right? Well, I've done this by the miracles of television. I've gone and done that already. Sometimes whenever you run application commands in Mona, they come back really quick. Sometimes they come back really slow. So if you're doing a presentation like this and you say, Mona, jump, it'll come back pretty quick, and people won't be staring at you for a long time. If you go and say, Mona, ROP, right, and that's where we're trying to get to, you might as well tell everybody to go get some coffee, come back in an hour, So yeah, you definitely want to think about that whenever you're doing this type of work. So I did some of this beforehand, and what I want is, I want to know about the jumps. So in my files, I have a jump.txt file that I had Mona create, and if you go down, you'll find that there's all of these jumps here. Right? All of these jumps. Now, the interesting thing about the way Mona goes and looks for things is it goes and says, hey, if this library or this DLL has any type of exploit mitigation properties, I don't really want to look in them, right? If a DLL has ASLR turned on and the memory addresses are always changing, that's no good to me. I need to have addresses that are reliable, right? Now, all of the OS DLLs in Windows 7 are all ASLR. They're changing all the time. So I can't use those. Not very interesting. This application has multiple libraries that got shipped with the application, and they are all, for the most part, safe for me to use because there's no memory or exploit mitigation properties compiled into them. Makes it very easy to do this type of work with this application. So there's actually this one file that library you'll see come up over and over and over again. It's configuration.dll. There's no mitigation on at all. No rebase, no safe SEH. If you keep looking across the screen, no ASLR. So we're going to just take this jump ESP, this memory address, and we're going to throw it into our script right here. Now, what I need to do is I need to pack it because the x86 architecture is little endian, which means it flips all the bits backwards. So I can either go through the painstaking task of flipping my bits and making a mistake while you guys are watching, or I can just use pack and have it do the work for me, right? Okay, so now I should get my application to go and execute that jump. Now, did I put the jump in there? I didn't inject any type of code so far, right? This is really important as far as ROP is concerned. What ROP is the art of not injecting code into the application, but still having control of the application itself. So what I've done is I found an instruction that already exists, something that I can use all the time. And I'm going to tell it to go and execute this code. What I'm also going to do, let's just go back and look at the application again. We have a series of C's, right? And I need to, I have a series of C's. And I need to figure out how much of a distance there is between where that command is, where that memory address is, where I'm controlling EIP, and where ESP is pointing at the moment, right? Because what I'm going to do is I'm going to want to put some code in there to execute. Now I'm kind of stepping away from ROP for a minute with this this demonstration, just so that you can see how this one ROP instruction, in a way, this one gadget is going to help me out. Okay, so I'm gonna. What do I have? I have 1, 2, 3, 4. I have 16 C's in between. So I'm gonna put that in my script so that we know. We can also put some instructions in there. So I'll just say D for the sake of argument, because I'm on a roll now. And I'm going to also throw in to the payload, I'm going to throw in hex CC. Anybody know what hex CC does to a debugger? It pauses it, right? Yep. Okay. And I'm going to just throw 4 of those in, right? 1 is good enough, right? But I'm going to throw 4 in because it'll look pretty. Okay. Oh, yeah, thank you. Good job. Okay. Okay. Let's check it out and see what happens. Start it up. Attach the debugger again. Right. And now we're gonna, actually, you know what? Before I load it, what I'm gonna do is I'm going to halt the oh, actually, no, with the halt the CCs, I was thinking ahead and didn't even think about it. Okay, so I'm gonna accept these exceptions that have nothing to do with my, okay, so what just happened? Do you guys see what is on the, in the instruction panel? We have CCs. How did that happen? I told it to go there, right? What happened is something that should never really happen in an application. I just told the application to jump and execute code on my stack, right? What you're seeing up here, those CCs and then the 43s, the int IEBX, that's the stuff I put on the stack, right? Those aren't instructions. That's my playlist, right? So now I have control. I can do whatever I want. I can execute because I got that int 3, that interrupt 3 to execute. So what am I going to do? I'm going to go back and I'm going to add shellcode to this particular exploit because it's pretty easy, right? Where did I get this shellcode? Anybody know? Yeah, I have no idea where I got it. Yeah, I have no idea. So I don't know what it's going to do, right? Okay, so I need to get rid of these C's first, right? I'm going to... the reason is because I am trying to see what's happening in the. I'm trying to see what is happening in the memory space while I'm doing this research, right? Because whenever you are affecting things in the application, you need to know how you're affecting it, and you don't know before it happens how the memory is set up. When you start out, you just know there's a vulnerability. You know, you see it on exploit DB, you see it in a CVE, right? It says there's a vulnerability, and then you do some more research and it says, oh yeah, if you throw so and so into this, it's going to crash it. And then you're like, oh, it crashes it, yeah. You know, how can I take control of it, right? I'm about to take control of it, right? Really, really well. Okay. Oh, I'll get to that. Yeah. Yep. Yeah, the interrupt 3 is telling the debugger to. That is a way of. Yeah, that is a breakpoint. But I think it's not the breakpoint that you were thinking of. But I will show you that in a minute. So a minute ago when I hesitated and I said, oh, you know what? I don't even need this. When I hesitated and I said, oh, wait, I need to do something else, I was thinking, oh, I need to go and set my breakpoint, right? Did anybody just see what happened? I popped my shell, right? That's easy. That's it, right? Did I use ROP? So, okay, yeah, you guys are too kind. Okay, so I popped it, right? That was easy. Now my foot's wet, right? You guys can do that. Anybody can do it, right? If you got the right application. Just do it 5 times. Make sure that you can get comfortable doing it, right? It's really easy. Okay, so now let's dive in a little bit deeper, right? So if I go back to my slides real quick. So we found EIP, right? I talked about pattern create. So there's this interesting thing called structured exception handling. And what it is whenever a good developer writes code, they will write it so that they know that there's going to be this particular thing that happens, right, in the code, and they know that sometimes it might not successfully do whatever it's supposed to do, right? So they create an exception for it. Cool, right? So I'm going to try something, and if that do something doesn't work out, we're going to try to catch that exception, and then we're going to do something else. If everything's fine with the first do something, then it just keeps on going. It totally ignores the catch. But if something bad happens, like EIP gets shoved with 414141, then we probably should do something about that, right? Well, interestingly enough, with this particular application, when I did that, when I threw the 4 ones into EIP, an exception occurred. Let's check it out. So I'm going to go back. And, I love the color of the command shell. I just have to say, that's a beautiful thing, right? That's not supposed to happen. But, hey, whatever. That's cool. Okay, so I'm going to start it up again, and I'll pay later. And I really have to try to figure out how to get rid of that. So I'm going to attach to it. And I'm just going to go through this again, right? And actually, you know what? Let's create a totally different file. Pop back over. And this time, I'm going to have a different script. And it's called exploit_sh, right? Does it look familiar? Yeah, it looks a lot familiar, right? It's the same script that we started out with. This time, the only difference is there's 700 bytes instead of 1,000 bytes. Why? Well, in this case, it really doesn't matter, right? In some cases, it might really matter because what will happen is sometimes you can do certain things with certain size payload, but let's say you want to throw an exception, right, and take over the exception handler. And for some reason, if the payload is too big, that exception never occurs because maybe something else handled the fact that your payload's too big. So I'm just going to pretend, that I have to have a payload of 700 instead of 1,000 to, initiate the vulnerability in this application. And what I'm going to do is I'm going to create this file, right? So we've got a file of A's, 700 of them. Go back. This time, what we're going to do is we're going to pass the exception past the point of EIP being filled, right? Okay. We're up and running. I'm going to go and open it up. We crashed. Okay. We're going to get to the point where EIP is overwritten with 4 ones again, right? We just saw this. This just happened. But the thing I didn't do before is I didn't look at the exception handlers, right? I overwrote the exception handlers for this. So this application is good, right? In a way, kind of. It knows something bad happened, right? So in this case, something bad happened, so the exception should be, go do something to fix it, right? But here's the bad thing. I overwrote that too, with less letters. Like, really? Come on. So now what do? We're going to do the exact same thing as we did before. We're going to do the pattern create. Everybody keeping up with me? That's excellent. Awesome. I love it. So this time I'm just going to say user share, Metasploit, tools, exploit, pattern create, right? Our friend pattern create from Metasploit, 700. And we're going to throw it into the script. Wow, that's pretty trippy. Here, let's just do that again because I have no idea what just happened. Okay. So now my file should have, oh, this is just not going well. I apologize, guys. This is the reason why you don't do live demos. Right? Apparently. Okay. Oh, and that is, okay. I did prepare for this. I had an original. Yeah, right? Yeah, okay. So this is the other thing that's bad about this is the fact that, you know, you try to do something cool like this in under an hour, and that never does. There we go. Okay, so now we should have our pattern. I'm going to throw that in my payload. While I'm doing this, do you guys have any questions while I'm trying to recover? Okay. Okay, here we go. So here we have a new file, right? And it should have our pattern in it. Now we can go and open this up again, and we're going to find out what the offset is for this exception handler. Okay. Okay, so here's the point where we were at before we overwrote EIP. That a memory address should be the same, right? Because it's the same point, 260 characters into the payload as we had before, right? Now we're going to actually look at the exception handlers, and now the 41s are different, right? We've changed what's in the exception handlers. The nice thing about the way the exception handler works on Windows is that you can use a gadget called pop-pop-ret to be able to take control of that particular data structure, which is the exception handler. So what we're going to do is we're going to go back to Mona, and we're going to say, Mona, I want to know what the offset is of this lower address. So the way that the exception handlers actually work is there's two parts of each record. The first part is a pointer to the next record. So if you think about it, think about this. Whenever you have an exception, there's the part where, you know, if the exception occurs, there's the catch part, and it goes off and, you know, it's supposed to go do something. That is the exception handler itself, and there's a pointer on the stack that points to that code to go and do that, right? And then below that, or right above that, there's a pointer to the next exception handler. So if the way it should work is that for some reason, if that handler fails, what do we want to do? We want to go to the next next handler and have that, take care of what's going on. And if that fails, let's go to the next thing. And the nice thing about Windows is the fact that there's an exception handler for the OS, right? And if you hit that, your application just crashed. It just disappears, right? So that is the reason why applications crash a lot of the time, is because the exception handler process tried to deal with whatever's going on, and then it got down to the bottom, and it naturally occurring, not what we're doing here, of course. The operating system says, "Oh, you just hit my exception handler. I'm shutting you down, right? You're going down now." So we are going to take advantage of this functionality and redirect execution flow because of it. So I'm going to go and take the offset of this lower address, which is actually the pointer to the next record in the chain. This one up here, the 41347541, that is actually the pointer to the exception handler itself. So what I need to do is I need to remember the pointer to the next record, which is the lower one, right, for something I'm going to do in a minute. But also this upper one is interesting to me because I can use that to do kind of what I did before. I can go find a memory address that has a pop right in it and redirect the flow of the execution of this application. So I'm going to go and ask Mona for the pattern offset, and I'm going to say 33754132. And the offset is 608 bytes. So I'm going to go back, and this time I'm going to go and say 608 bytes into it, right? Pre-SEH equals 608 bytes, right? And what I want is this to be pre-SEH. And then I'm going to write my A's or my B's to overwrite the pointer to the next record, right? And then I'm going to put C's in to overwrite the pointer to the exception handler itself. And then I'm going to just finish it out. Tail size equals total minus the length of the payload. Yes, thank you. So do you guys know why I'm saying, doing this last bit? Why do I keep doing this here? The tail size. That's right, yes. I want to make sure that my payload stays the same size. So I'm going to, exactly. Because if I make the payload too small, I might not overwrite something to trigger the vulnerability. Yeah, sometimes you can, yep. It depends on the application. This is all dependent on applications, right? Every application that you look at is going to be completely different. This one, I think that you could probably write thousands of bytes into it, and it doesn't care. Okay?
Is there any good way to estimate how much you could put in without breaking something, or is it pretty much trial and error?
Yeah, it's called fuzzing, trial and error. Yeah, good question. There's another application that I gave to the class for an exercise yesterday, and I didn't tell them how big of a buffer they needed, right? How big of a payload they needed, and I said, hey, start with 10,000 bytes and just keep on going until you crash it, right? Because the application is just going to say, oh yeah, that's cool, I'm going to ignore you. And then you're going to send it, more bytes, and it's going to say, hey, I'm ignoring you again, right? And then you're going to get to this one point, it's going to like just, right, just crash, all, melt all over the place. Okay, so now let's see if we overrode the exception handler here. Okay, here we are. We overwrote the EIP with 41s, and here we see that we indeed have 42s in the pointer to the next record and 43s in the exception pointer to the exception handler. So we've won control again, right? We're back in the same situation. What can I do here? Well, the thing with the exception handler on Windows is to take advantage of this. We want to be able to sort of pivot like we did before. Before we kind of pivoted from, running instructions normally to running instructions off the stack. So what I'm going to do now is I'm going to use a pop-pop ret, and that's going to allow me to kind of pivot execution back to the stack, right? And a gadget, when you're dealing with ROP, is normally some type of series of instructions followed by a ret. So a pop-pop ret is a gadget, as far as ROP is concerned. So with this, we're definitely getting into ROP territory. It's a simple one, but we're still doing it. So let me just go and back and look for a ROP or a pop-pop ret. So in Mona, in Immunity Debugger, I could go and ask Mona, I want to know where pop-pop rets are. And there is a command called SEH, right? Because we're dealing with SEH at the moment, makes it pretty easy. When you run it, you'll get a file called sch.txt. And in there, if we go down, we will find all of these pop-pop rets. Look at them all. There's tons of them. Let's see how long this thing is, right? SEH. Thousands of pop-pop rets that we can use. So we can pretty much, grab any one of them that we want. Oh, man. I am way out of time. Jared. Sorry, man. Okay. So this first one, should I use it? No, I can't use this first one. Why? Because this application doesn't allow me to use hex 00, right, in my payload. If I tried to use it, it would just mess me up. So I'm going to use the next one. I'm going to use this one. Go back. What was that? Somebody asked why?
Yes, I asked why.
Okay. Why? Okay, that's great. Great question. There are bad characters for some applications. Some applications don't like hex 00. Does anybody know why an application wouldn't like hex 00? It's a null byte. It's a string terminator, right? Yeah. Right. So with this application, guess what it does? It reads in the playlist as a string. Right? And it terminates. So if my payload has a null byte in it, then it stops reading at that point. My playlist is that much shorter, right? So I have to pick this next instruction because there's no null bytes in it, okay? So what I'm going to do is I'm just going to go in and do the same thing as I did before. And why am I using struct pack? Does anybody remember? That's right. This is a little Indian, so we need to deal with it accordingly. Okay. So the other thing I'm going to do for time's sake is I'm also going. So I overwrote. I put the pack in the spot where the pointer to the handler exception handler is, so that I can execute my pop-up ret. The other thing that I'm going to do, that is going to cause the behavior of SEH to actually move ESP, allow me to jump to the point where the pointer to the next record is, which is the 4 bytes before that, where my B's were. And what I'm going to put in here is I'm going to put a jump 6 bytes, because what I'm going to do is I'm going to pop ret, kind of pivot onto execution onto the stack, execute my jump 6, which will allow me to jump over the gadget that I have here, my pop ret, and then I'll execute my shellcode. So what I'm going to do here is I'm going to put EB06, which is in machine code, a jump 6. So remember that. There's going to be a test later. And then I'm going to also put 2 nulls. And the reason why, or not nulls, I'm just going to put 2 nops in there. And I'm putting those nops in there because I just need to fill some space, right? Because there's 4 bytes that I have to fill for that particular record. And then what I'm also going to do is that since I know this is going to work, I'm just going to go and grab my shellcode again, right? And I'm going to put it into my script. Okay. And if I put it right here, I'm actually going to put some nops in here as well, just so it gives it a little bit of a nice landing. The reason you put nops in is to make it so that you can allow the CPU to kind of slide down the stack, right? Sometimes you don't know exactly where the CPU is going to land. Right now we know because I'm jumping 6 bytes. But if we don't know exactly where we're going to land, putting a nop slide in there actually gives us a bigger landing to land in. So I'm going to put that in there. And then after that, I'm just going to put payload plus equals my shellcode, right? Okay. And I'm going to execute that. And if, oh, I must have done something wrong. Oh, yeah. No, maybe my shellcode is longer than, let's see, hex dump. It looks fine. Let's see what just happens and go from there. Okay, so we're going to go back and start it up again and see if it crashes. Yep. Okay. So what just happened is we got 2 shows for the price of 1, right? Very cool. And what's really nice about this particular exploit is it cleans up the application, right? I don't even have to close it out. I mean, that's really nice. And I got 2. And they're persistent too. This is actually something that's particular to this one application. So what is ROP? ROP is, it is where you go and find a series of instructions that have a return at the end. And the reason for doing that is so that you can put, like I did with the pop ret, I go find the pop ret, get that memory address, and put it onto the stack, right? And then what I do from there is I continually add, different gadgets to create a program that I want to do, right? The interesting thing about ROPing is it has been proven that is nearly Turing complete, meaning that you can pretty much do anything that you want, as long as your gadgets are plentiful enough to do it. Now, the interesting thing about this application is when you ask Mona to ROP, it goes and finds all the ROPs in the space. And when you're looking for gadgets, gadgets in the memory space of the application. And when you are looking for gadgets, you're not looking for gadgets in the normal way that you think about it. What it does is it goes and looks for the machine code for a ret and then works backwards to see if there's the possibility of creating a series of instructions that would help out in ROPing. The reason for doing that is because the x86 architecture has multivariable length instructions, right? It's kind of like taking a long paragraph, right? And taking out all the white space and mashing those words together, right? You can still tell kind of what the paragraph said or the sentence said originally, right? But if you go and look at specific spots of the paragraph without reading through it, you'll find other words in there, right? In between the real words that were there before. Can you visualize that, right? When you look for gadgets, you're doing the exact same thing. So sometimes it's funny when you're in the debugger, you're picking a memory address that's not really, the right memory address for the application code, but it starts a gadget with a return at the end, right? And the debugger goes crazy because then you see a bunch of other instruction past that gadget that make no sense. Like there would be no way there'd be instructions like that. But it's just because that gadget actually falls in between the real instructions, right? So that's what ROPing is. Like I said, ROPing, the gadgets are normally end in returns, but that's not always true. You can have gadgets that have any instruction at the end that will get you back to, executing the next address, just like a ret. So if you had a jump ESP, that would work as well. Yes, sir.
So with when you have your payload, is it basically you're going to these gadgets and then you're supplying arguments? Like, so if you want to push arguments onto the stack, I mean, is that inside of the ROP or is that inside of your payload?
When you're ROPing, you're going to find a bunch of memory addresses that do different things. And those memory addresses are in the other DLLs, more than likely, right? Like configuration.dll, right? That's a gold mine for this application. And what you do is you say, you know what? I need to do a certain thing. I'm going to find the memory address for a series of instructions that do that for me. And I'll have an example in a minute. And then you just put those on the stack. So you're not putting instructions on the stack. So, like the difference between the pop-pop-ret and the jump 6 that I had, the first one is a gadget. That would be a ROP, right? Part of a ROP. The jump 6, that was an instruction I put into my payload. When I ROP, I want to not put any instructions in. I only put memory addresses on there, okay? So here's my first example, or my only example. I took my other example out, actually. So what did we say? We said that no bytes break this application, right? So I can't use a no byte. What if I have to push something that has a no byte onto the stack? For instance, this 201, and I need to move it into EBX. What do I do, right? Let's ROP, right? So I found at memory address 6404 C268, more than likely being in configuration.dll, a pop EAX and a return. Is that a gadget? Yeah, it is, because it's an instruction with a return at the end, right? So what should I do with that? I'm going to take FF, FD, FF, and put it right under it. So in my payload, right, I have my A's, my A's, my A's, my A's, and then I have this first value, 6404 C268, and then after that I have FF, 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 or FD, FF, right? And then I need to negate it. Why? Because if I need to negate that value, it becomes my 201. Did I have to put any null bytes into my payload? Nope, I didn't. Did I put any instructions in my payload yet? No, I didn't, right?
Could you use arithmetic as well?
Yeah, As long as if you find a gadget that's an add in your, then you can use it, definitely. Yeah, man, definitely. Go ahead.
What are the advantages of doing this versus like the interpreter where they'll pull the back characters out for you?
Oh, actually, whenever you ask Mona to ROP, you can say, Mona, ROP, and I want to only use characters that are good for me. So I can tell it what bad characters are, and then it will only find gadgets or make suggestions of gadgets that do not have those characters. Great question. Thank you. I appreciate that. And then the last instruction, right? Memory address 6164-1C70. There's an exchange EAX EBX. What does that do for me? That puts my 201 into the EBX, register, right? I've accomplished my goal. I have not put any code into my payload. I've only put memory addresses in there, right? The neat thing about this is if I know that there's multiple memory addresses with each of these types of instructions, right? I could make it so that it changes my payload every single time. So why would I want to do something like this? Well, there's something called dep, right? Dep is kind of a pain, right? Because what does dep do? Dep makes it so that you can't execute code off the stack. Yeah, that sucks, right? Well, Microsoft gave you a solution for that. It's called Virtual Protect and a bunch of other OS functions. Virtual Protect allows you to turn no execute off on certain pages of memory. What do we want to do with that? I don't know. Maybe turn off make the stack no execute. I mean, make it execute, right? Executable. We can use Virtual Protect to do that. Why did I have this example here, that 201? Well, for Virtual Protect, maybe my shell code is 201 bytes long. So what I do is, with Virtual Protect, you need a couple things whenever you call it. You have the return address. It's the location as to where Virtual Protect is going to return to. That's going to be where my shell code lives, right? And then there's the LP address. That is where I want to change my address permissions to execute, right? That's going to be the same spot, the shell code. And then there's a couple other things that we need to do, right? We need to define execute read write, which is the 40. It's the same thing as before. And then there's this weird thing at the end. I don't really know why that function needs it. And then to do it, originally, if I had had time, I was going to show you how to use pushAD to put all of the information to execute Virtual Protect onto the stack by using pushAD. That would be an exercise for you guys at home. Is there any questions as far as ROP is concerned? And getting your feet wet, and hopefully a little bit of what I've shown you gets you to want to try this out.
What exactly is the function of pop-pop ret?
For the pop-pop ret allows you to pivot the execution from the normal area of memory to the area on the stack, only when you are trying to exploit SCH. Because what it does is it moves execution or points execution to that pointer to the next SCH record, which you have control over. Yep. Yeah, no, that's cool. Yeah, if you have questions, please come and ask me. Yep. Thank you very much. Yes. Thanks a lot.